Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now.
According to the general theory of relativity, gravity isn't a force, and there are no gravitational fields. It's kind of like an illusion.
Wait, what? No gravitational fields? How does that even make sense?
Let me explain. So, Albert Einstein once said that the happiest thought of his life was imagining a man falling off a building.
How is that a happy thought?
It's kind of like, not really, but it's like Schadenfreude.
What?
I don't know if I'm pronouncing it right. I'm 100% butchering it, but
Yeah.
Schadenfreude.
So, you mean like laughing at videos of America's biggest fails?
Yeah, exactly.
Oh, okay. So, for all of you, basically, Schadenfreude is a German word that describes the feeling of pleasure or joy that you get from learning about another person's suffering or like humiliation. So, getting back to Einstein, what basically made old Albie so happy was realizing that this man, while falling, he wouldn't feel his own weight and he would be weightless.
And anything he dropped on the way, like for example, he was on Instagram on like watching some reels, and he just drops his phone on the way down while he's falling. It would remain stationary relative to him, or it would move in uniform motion, like constant velocity.
So, it's like he's floating, right?
Exactly, the situation would feel the same as if you were in deep space as well, far away from any large masses, with your spaceship at rest or coasting at a constant velocity.
And you wouldn't even feel your weight in that case either.
Exactly, because objects would remain stationary relative to you or move in straight lines at a constant velocity even if you give them a push. You would, like by definition, be an inertial observer, not accelerating and not in a gravitational field. All the laws of physics you will apply to your reference frame.
And there's no experiment that you could do to tell your frame of reference apart from any other one, right?
Any other initial one, exactly.
Yeah.
So now here's the leap Einstein made. He said that these two scenarios, the man falling off a building and the person floating in deep space, they're not just similar, they're equivalent.
Like exactly the same.
Yes, like exactly the same, physically the same. That means the man falling off the building is not in a gravitational field.
What? Of course he's in a gravitational field now. He's next to the earth.
Yeah, I get what you're saying, like he's getting attracted by the gravitational field of the earth, exactly, but Einstein's equivalence principle focuses on the experience of the observer, like what those two guys experience, like the man falling off the building, what he, in his own perspective, experiences, and the space guy, obviously. So, for both of them, they feel weightless, so they are an inertial frame of reference, just like the other, like each other, right? So they both are in inertial frames of references.
But the man's speed is increasing by 9.8 meters per second squared. He's accelerating, and that would be very evident when he falls to the earth, no?
Yeah, that's true. But it looks like an acceleration to an external observer. But in his frame, as I said, we're looking from his perspective, he's weightless and inertial.
Okay, but what about the rocket guy? So, what if we imagine that he's drifting at a constant velocity and he suddenly comes near a planet? Wouldn't the path of the rocket start curving towards the planet?
Yeah, that's right. You mean because of the gravitational attraction of the
Correct,
planet, right?
correct.
Simply. Good point. But that's again for an external observer. It would curve slightly towards the planet. But inside the spaceship, rocket guy wouldn't feel a thing. He wouldn't. The instruments on his ship wouldn't register any force or acceleration.
Even as the rocket gets closer and starts moving even faster.
Exactly, because rocket guy still feels weightless. For him, nothing has changed.
So when does his frame of reference stop being inertial?
That's the thing. It doesn't. It remains inertial until the instant it crashes. Like his rocket crashes into the planet.
So if we say that there are no gravitational forces or fields, how do you even begin to explain the rocket's curved path?
The answer is curved space-time.
Curved spacetime? How does that explain the rocket's path?
So we spoke about curved space-time in I think at least a bit in Black Holes episode 2 or 3.
Yeah.
So we'll just say that rocket guy was moving in a straight path, right? At least for him.
Yeah.
So he was moving in a straight line through space-time. The whole time he was doing that. But space-time itself is curved especially around massive objects like planets, and that's why it appears curved to a distant observer.
So it's not the path that's curving, it's the space-time that is curved, and even if he's traveling in a straight path, to an external observer it appears like curved.
Exactly. And the straight line paths through curved spacetime are called geodesics.
Geodesics.
Yeah. It's basically the same concept that airplanes use. Planes try to fly at the shortest route between cities. This is essentially a straight line, right?
Yeah. So the Earth's surface is curved, but those straight paths look straight to us because the Earth's surface is curved.
Yeah, and they look curved on the map as well.
Yeah.
So the shortest path over curved surfaces are geodesics, and in space-time, geodesics are the straight line paths followed by inertial observers.
So Rocket Guy's curved path is actually a geodesic in space-time.
Exactly. So let me give you and the listeners another analogy. Okay. So imagine you and I, we're standing 1,000 kilometers apart on the equator, and we both start walking due north.
Okay, so we're heading north. Then what happens?
So over time, due to the curvature of the Earth, and because it's a sphere, actually it's an oblate spheroid, but whatever. Exactly.
Non-Euclidean geometry.
Yeah. So over time, we will both. For us, we are going in straight lines, but over time we will come closer together, and eventually we'll meet at the North Pole.
But there's no force pulling us together. We're just walking straight.
Exactly. It's as though there's a force pushing us together, right? But neither of us actually feels a force.
Oh, so the force is like an illusion caused by the curved surface of the Earth.
Yeah, exactly. And that's how gravity works. It's not a real force. It's just a result of objects following geodesics on curved spacetime.
So astronauts on the space station are also weightless, which means they are inertial observers traveling on a geodesic.
Exactly. But their part does look like a circular orbit. Do you agree?
Yeah.
Because they are revolving around the Earth, right?
Yeah.
Now you might ask, why? How is that a straight line? Well, it only looks circular only if you know the time dimension. As I said, it's space-time, right?
Yeah.
You have to remember that they're moving through both space and time. The Earth curves space-time around it, so the straight line path appears as like a helix, like the double helical structure of DNA
Yeah,
helix, like that.
So their motion only makes sense when you consider space-time as a whole. Like you can't virtually separate
Space
it into
and time,
space
exactly,
and time.
exactly. So a lot of people visualize that with a bent sheet analogy, as in like you have a piece of, let's say, rubber, okay, and you're keeping a heavy ball around it, in the middle of it. So let's say you keep a bowling ball in a large sheet of rubber, and you roll a golf ball around it. So
Yeah.
obviously the golf ball will like rotate and spiral down into the center.
That's like the Earth orbiting the sun, right?
Exactly, and the moon orbiting the Earth. Exactly.
And your rubber sheet is basically what they call the fabric of space-time.
Exactly. So that usually leads people to think that the objects fall towards the middle of the well because of the gravitational force. But as we said earlier, in general relativity, there's no gravitational force.
Objects are just traveling in straight line paths through space-time. It's just that space-time itself is curved around massive objects, so those paths don't look straight to us.
So it's literally space-time's curvature that does change the paths.
Exactly. As John Wheeler once said, matter tells space-time how to curve, and space-time tells matter how to move.
That's wild, right?
Yeah.
But what happens if you accelerate, like on a rocket ship in deep space?
That's an interesting question. So imagine turning on the rocket thrusters to accelerate at 9.8 meters per second squared, like the value of g.
Yeah.
An outside observer would see that the rocket floor is moving towards the stationary objects.
And inside?
Inside, it would feel like everything is accelerating down towards the floor. You'd feel a force that is pushing up on your feet, just like the force you feel right now standing on Earth.
So you're saying being in a rocket, accelerating through deep space is the same as standing on Earth?
Yeah, exactly the same.
Wow.
So let me ask you this. Do you feel weightless now?
No, of course not.
Then you're not in an inertial frame of reference.
Yeah, fair.
Your situation is just exactly the same as someone accelerating on a rocket.
But we are at rest on Earth, right?
That's the thing. You're not at rest. You're accelerating. And there is no gravitational field.
No gravitational field again. How can that be?
Because, as you said, in general relativity, gravitational fields don't exist.
Yeah, that's true. But in this case, like how are we accelerating?
What you're experiencing is equivalent to acceleration in a rocket. It's basically like being at rest in a gravitational field isn't accelerating in a rocket, it is accelerating in space time.
So in standard Newtonian physics, we draw two forces acting on a person, right?
Yeah.
The force of gravity pushing you down, so mg, F is equal to mg,
Yeah.
and the normal force on the floor pushing you up.
Right. And since those forces are equal and opposite, there's no net force, so you're not accelerating. That's according to Newton.
Newtonian physics.
Yeah, correct.
So in general relativity, as we said earlier, gravity isn't a force, right? You have no weight.
So that's what's keeping me from falling through the floor.
Yeah. The only force on you is a normal force. Like, that's pushing you up, right? That means in general relativity, you're actually accelerating upward.
Accelerating upwards, but we're not moving up.
Yeah,
are
we're
we?
not flying, that's true.
Yeah.
But relative to what?
Relative to the floor, the chairs that we're sitting on right now, everything else in this room.
Yeah, that's true. But all of those things are in your frame of reference, right? And that's not inertial.
Okay, so in my frame, I'm not accelerating. But what if we checked with someone who is in an inertial frame of reference?
Sure, let's go back to our guy who's still falling off from the building, like Loki.
Yeah.
Like he fell. I think Doctor Strange made him fall for 30 minutes straight or something like that. Yeah. So this is the guy. The guy is falling off the building. He's doing that right now. Okay. So he would see you accelerating upwards at 9.81 meters per second squared.
Wait, hold up. So Newton actually rammed his head into the apple. The apple didn't fall into him. On his head.
Yeah. Like literally, you can say that. Yeah.
So acceleration is just a deviation from a geodesic.
Exactly. You can't follow a straight line path through space time because the floor applies an upward force on you, and that force makes you deviate from the geodesic. So you're accelerating up.
So if I'm accelerating up and so is everyone else around the world, doesn't that mean that the earth should be expanding?
Not at all. It is possible for you to accelerate even though your spatial coordinates aren't changing. So like you're not moving at all, but you're still accelerating.
How is that possible?
It's again because space-time is curved. Curved space-time is the answer to a lot of things, you know?
Yeah.
So let me show you how general relativity explains this.
Okay, but like keep it simple, please.
So here's the idea. The second derivative of your position with respect to time is your acceleration, right?
Yeah,
Simple as that.
correct.
So in flat space-time, this would mean your spatial position has to change if you're accelerating.
Makes sense so far.
But space-time actually isn't flat, especially near massive bodies like the Earth, right? And we're on Earth.
Also correct.
So when we take curved spacetime into account, there's an extra term in the equation related to the curvature of spacetime and your velocity to time squared.
So basically, what Einstein has done is just introduced an extra term into an equation, so that I don't need to change my position, but I
Position.
can still accelerate.
Exactly. So in curved spacetime, this is the breakthrough. You need to accelerate just to stay in the same place.
Oh.
So you are literally accelerating upward right now, even though you're standing still.
So that I got it now. Standing still in curved space-time requires constant acceleration. That's the beauty and the mystery of general relativity.
Like exactly. And a lot of this might seem more complicated than Newtonian physics, but one classical mystery becomes a lot simpler in general relativity. Why all objects fall at the same rate.
Yeah, I've always heard the Newtonian explanation like the only force on a free-falling object is its weight, which is like g/m by r squared, which equals its mass times acceleration.
Right. And then you cancel the object's mass on both sides of the equation, right? Leaving the acceleration same for all objects.
But isn't the real mystery why we can cancel those both m's?
Exactly. In Newtonian physics, the m on the left is gravitational mass, the property that creates and experiences a gravitational field. And then the m on the right is inertial mass, the measure of resistance to acceleration.
Right, they're conceptually very different properties. But why are they even numerically identical then?
I mean, scientists have tested that, right?
Yeah, down to 1 part in 10 trillion.
Ooh, that's a lot. Like, very precise and accurate, whatever.
Yeah, gravitational and inertial mass appear to be identical, but Newtonian physics doesn't really explain why they are.
So, how does general relativity solve it?
In general relativity, there's no mystery because objects aren't really accelerating.
Then what happens when they fall?
They're following straight line paths or geodesics through spacetime, which we talked about like just 2 minutes ago.
Yeah.
They only stop when they encounter something like, say, the ground.
And they only appear to accelerate because the floor or the ground is accelerating into them, just like Newton accelerated into the apple. You said that, yeah.
Yeah. So in the rocket, which we talked about, the objects seem to accelerate at the same rate, but they're not. It's the flow that is accelerating into them, not the other way around.
And that's like a very different way to think about it, right? But it works.
Yeah. And it was definitely that like
Crazy.
a crazy breakthrough
Yeah.
in 1915 when Einstein proposed it.
And like it was a crazy theory as well. Like for everyone, no one like thought about it as actually realistic.
Yeah. And that's why he came up with a measurable prediction to test his theory.
Wait 1 second. What prediction?
So it has to be something observable, of course.
Yeah.
So he proposed that how light bends around massive objects. It was his way of turning an abstract idea into something that scientists could basically verify.
So he thought about everyone and everything, right?
Yeah, he's Einstein.
Exactly. So imagine a rocket ship, the same rocket guy. Imagine him coasting to deep space. He was chilling around, okay?
Yeah.
So if you shine a light beam across a cabin, across like the rocket cabin, it'll travel in a straight line because light is light and it travels in a straight line and it'll hit the opposite wall at the same height as the source.
Correct.
That makes sense because light moves in a straight line. But what if the rocket is accelerating?
To an external observer, the light still travels in a straight line, but inside the rocket, something different happens. During the time it takes the light to cross the cabin, the rocket is speeding up, right?
Right, because it's accelerating, exactly.
Yeah. So by the time the light hits the opposite wall, it's ever so slightly lower than before. In an accelerating frame of reference, light bends downward.
But the effect is small, and even if the rocket is accelerated at 10 Gs, like which would
Probably kill us.
exactly the deflection would be about the width of a proton. Okay, so it's like very less, but it exists. Okay,
However minute this may be, it still
proves the point. Exactly,
An accelerating frame bends light.
that's right. So Einstein extended this reasoning to suggest that light would also bend when passing near a large mass, like black holes, for example, as we spoke about earlier.
And the only place where we can find a mass big enough to test this is our sun.
So we tested this. We, as in scientists, long
Yeah,
ago
yeah.
tested it because they wanted to observe the light from distant stars passing close to the sun to see if it deflected.
But the real problem was, how do you see stars right next to the sun? It's so bright.
Yeah, you wait for a total solar eclipse,
Oh.
and that's smart, right?
Yeah.
So that's exactly what happened in 1919 when Arthur Eddington set out to take photos of stars near the sun during one such eclipse.
And what did he find?
So he found that the positions of stars appeared deflected by the precise amount Einstein predicted in his general theory of relativity.
Oof, that's incredible. So was the deflection the same as what, say, Newton's theory would have predicted?
No, it was actually twice the deflection that a strictly Newtonian model would calculate.
So this was basically a big confirmation for general relativity.
Yeah, it was like a big win, like absolutely. So general relativity actually has passed like virtually every single experimental test over the last like 100 years.
But it could also crumble very, very fast if that
CPT, yeah.
the charge parity
Parity time.
time symmetry that we spoke about earlier, that
previous episode,
failed.
yeah.
If that fails, everything,
Yeah,
everything
including
fails.
quantum field theory, yeah. But there are still more tests to do.
For example, we know that accelerating charges radiate electromagnetic waves. This was originally proposed by James Clerk Maxwell in his theory of electromagnetism.
Exactly. So exploring these phenomena like what you just said, accelerating charges radiating electromagnetic waves is one other way to test and refine our understanding of relativity.
And here's an interesting thought experiment to test the nature of gravity. Imagine comparing the behavior of a stationary charge in a gravitational field to that of a free-falling charge.
So in a more Newtonian view of gravity, the stationary charge shouldn't radiate electromagnetic waves since it's not accelerating, right?
Yeah, but the free-falling charge is accelerating. So Newtonian physics would predict that it should radiate. But what would general relativity say about this?
General relativity sees things differently because in general relativity, the free falling charge isn't accelerating. It's just following a straight line path through curved space-time. Exactly, right?
So the charge that we thought that is stationary is not really stationary, and what we thought is accelerating is not really accelerating.
So the charge is actually considered to be accelerating in general relativity because the floor or the surface is pushing up on it to keep it stationary.
Correct.
So in this view, it's the stationary charge that should radiate electromagnetic waves.
But has anyone ever experimentally verified this?
Not yet. Logistical challenges, blah blah blah. Logistics have prevented it so far, but it is a fascinating idea.
So, what do you think will happen? Whether the free falling charge radiates or not depends on how you view gravity as a whole.
Yeah, exactly. If you believe the free falling charge radiates, you're leaning towards a Newtonian perspective. But if you think it doesn't, then you're aligned with general relativity, where gravity is seen as an illusion.
That really makes you question the fundamental nature of gravity, which comes back to the very title of our episode. What is gravity?
And that's the beauty of these kinds of thought experiments. They literally force us to confront what we truly believe about the universe.